for that embarrassing introduction. It's very kind of you. And thank you for having me here. And I'm going to tell you a bit about my recent explorations in can AI do pure mathematics? And indeed, this is very much in line with the question, what is creativity, right? Which I think is a quite topical thing. And I got into this whole thing because of fundamental theoretical physics. I mean, by training, I'm a mathematical physicist. And I just want to give a couple of slides on like how this led me to think about this kind of problem. So the 20th century, of course, was a great century for science, and in terms of fundamental understanding of the structure of space-time and interactions. So, but the point, from a mathematical point of view, what that is there has been this dialogue between pure mathematics and fundamental physics. So things like in algebraic differential geometry and topology or representation theory of groups has been clearly recognized by people like Einstein and Dirac and Feynman to be the right language for physics. If you want to understand the structure of reality, you have to understand the structure of pure mathematics. So this has been established for 100 years. Well, it really goes back to Newton's Principia, and this is well studied. So just to give you a few examples, gravity, if you want to think about gravity it's a Ricci form of tangent bundles, elementary particles, irreducible representations and sections of bundles, etc., etc. By training, I was a string theorist, and really what you think about string theory, whatever it is a unified theory of everything that is a brainchild of this, what we call the gauge gravity geometrization tradition that goes back to Einstein. Right? So that's the 20th century. We're in the 21st century. So there's something very special about this century is because we've added a new thing to this dialogue. Now it's not, well, you can't really call it a dialogue anymore. You can try to call it a trilogue if you want. So there's pure mathematics, fundamental physics, and there's this new idea of computation. And why is that? Okay, so I'm going to give you one slide of string theory, what string theory is, and how this led to this problem in computation. So string theory is this theory of quantum gravity, the supposed unified theory of everything that lives in high dimensions. It is a theory that lives in 10 dimensions that purports to unify all of the fundamental interactions of nature. There's no experimental evidence for this for string theory yet. It may take 200 years, but if there is a single one, then in some sense we're finished with physics at some level, because that is the ultimate answer of Newton and of Einstein, of Galileo. We have a fundamental theory of everything. But of course you may object to the fact that we don't live in 10 dimensions of space-time. It is pretty obvious that we live in 3 dimensions of space and 1 dimension of time. So string theory's biggest theoretical challenge, I'm not an experimentalist, I don't know how to resolve this problem from an experimental point of view. The theoretical point of challenge of the string theory is that we have to somehow reduce 10 dimensions down to these 4 dimensions of space-time that we see on a global scale. Right? So we're missing 6 dimensions. And the indisputable equation of string theory is 10 is equal to 4 plus 3 times 2. Right? This is, I think everybody's happy with that equation. So we're missing the 6 extra dimensions. Right? So how do we study 6-dimensional space? So that's where, where many of my colleagues and my old PhD supervisor, we're all coming to study the differential geometry and the differential topology of 6-dimensional spaces. So now it's a pure math problem. It's a very nice problem because in some sense it answers Kepler's very old statement, ubi materia, ibi geometria, where there is matter, there is geometry. Right? Of course, Kepler said this in a very mystical point of view. But string theory, what string theory does is that each 6-dimensional manifold gives a different type of universe. It may not be the universe that we live in, but it would be very nice to find a geometry which reduces completely this thing that gives us a particular universe. Okay, that's basically the paradigm what's called string compactification. So, but there's a catch, right? There's always a catch. And the catch is there are simply too many geometries. This is a very interesting problem in pure mathematics. In 1 dimension, if you talk about a 1-dimensional manifold, there's not much choice. It's either a line or a circle. Dimension 2 is already getting a bit tricky. You can have a surface of a sphere, you have a surface of a donut, and so on and so forth. In dimension 6, there is a lot. In fact, it's not even classified. We have no idea how to even classify. It might be Turing incomplete. We have no idea how to even approach this problem. And so far, the number of possible candidate geometries in 6 dimensions, we're getting to numbers like 10 to the 500 and 10 to the 10 to the 5. Okay, this is just a mathematical fact. It has nothing to do with physics. It's just that in 6 dimensions, we have a lot of more possible ways to play with geometry. So when it comes down to a philosophical problem, is our universe probabilistic, anthropic? Possibly. Is our universe one of its own kind? Are we special? Or are we just one of possible multiverse? And I don't have an opinion on this. I tend to go for number 2, just because it's pretty. But we certainly have not found, as a community of fundamental physicists and mathematicians, we have not found a special rule while our universe is special. And this should be really contrasted to NASA's exoplanet search, right? NASA has searched through now something like 10 to the 4 number of planets outside of the solar system, and they're looking for one that looks like Earth. Is there a selection principle why Earth is special? And what I like to do, which really impresses my 8-year-old daughter, which is what I do is I try to select for our universe. That's what I work on. Is our universe special in this possible multiverse of 10 to the 500 and 10 to the... This is what's called the landscape problem of string theory. So, well, fine. When you get to this problem of this large numbers, you really have to think about something new, right? You can't write down, blackboard computation is not possible anymore for this kind of problems, right? When it's dealing with this kind of large data. So, as I said, I won't bore you too much with the details. Is that then as I got thinking is when I started learning as a complete novice the field of machine learning. When you're dealing with this kind of numbers, can we machine learn this space of possible geometries? Initially, since I'm a novice, I had no idea what to do. Classically, you know what to do, right? So you go through, in fact, there's this little blue bubble is supposed to be clickable, but since it's not clickable, which is even better, so you don't have to see the details of the computation. You can represent manifolds and geometries in terms of matrix representations of multi-degree. And there are classical methods in algebraic geometry which teach us how to compute topological invariants. This is fine. The problem is that any such computation in algebraic geometry, I think my very good friend and colleague Heather Harrington, who was here yesterday, and I think she might have given you a very good overview of algebraic geometry. The heart of algebraic geometry computations is that the Grobner basis computation is double exponential complexity. So you can't do to linear algebra, which is n log n essentially, and you can't do that to differential geometry, which is double complexity. So fine, so I just said, well, fine, let's just start feeding manifolds into a machine learning program. I used a very simple forward feed neural network. And that's what this paper I did in 2017. As a complete novice to this entire field, that's why I'm here today. I'm here completely as an outsider, so you can forgive my ignorance. This is great. I love saying this because people are gentler to you when you say that I'm a complete novice. But I start playing with this, toying with this notion, is it possible to do algebraic geometry as a problem of image processing? Like that, this field of algebraic geometry. And I was very surprised to find out that if you feed a neural network, even a very simple forward feed neural network, say 10,000 manifolds with some topology that's associated, whose classical computation will take double complexity to accomplish. If you feed that into this neural network, it learns within a number of minutes and start predicting new topological invariants for manifolds it's never seen before. So somehow, a very simple neural network is doing algebraic geometry without knowing any mathematics to 90+ precision. I mean, of course, it's not good enough for mathematical point of view, but it might be good enough for theoretical physicists. Because 90% precision in the space of 10 to the 10 to whatever could potentially start selecting for you the correct universe in which we live. That's a practical solution. Right? So this got somewhat string theory into the era of big data. Right? But for me, as a mathematician, it got me thinking about something a little more, right? Why is it that it was doing so well? How is it possible something that is a double exponential complexity problem in pure mathematics, it can be essentially guessed by a very simple neural network, right? I'm not giving you an answer because I don't have the answer. Hopefully, I know I've misled you thinking that I will give you an answer. I have no idea, but I hope that this will encourage this community to start thinking why this is possible. So this really gets me thinking about what this paradigm is for the AI mathematician. So let me go right back. So let me give you this pattern, right? Mathematics at some level is about pattern recognition. I think everyone in the audience can immediately tell me what the next number is. Yes. So this is just simply divisibility by multiple of 3, okay? What about this one? I'm not giving any prizes because I'm not carrying any cash on me. It's a little harder, right? So this one we can discuss later. This one is the set of integers going up, whether it's prime or not. Okay, you're already struggling a bit, but if some of you are like obsessed with number theory, you might be able to spot that. What about this one? I will actually give you money if you can tell me what the next number is. I mean, of course, I've been very, cheeky. I've only given you a very short segment. Even if I gave you 1 trillion of these, I bet you won't be able to tell me very, very easily. So what this is the parity of the number of prime factorization given the sequence of integers. This is called the Liouville lambda function, and it contains some of the deepest results in number theory. There are statements of this sequence which are equivalent to the Riemann hypothesis, the most difficult problem in mathematics. So, okay, fine. But as a data scientist, what should we think? Is it possible, one, for neural networks or the likes of or support vector machines to try to predict patterns of such a type? And if not, is it true that the AI mathematician would struggle as much as the pure mathematician? And hence give some sense of a benchmark of what mathematics actually is and what creativity is. Okay, fine. Well, let's try some simple experiments. These are, the way that I've written these, they're binary vectors, right? So it's a very nice representation, it's ones and zeros, right? So one thing I can do is to label them. So fine, so I have this sequence of zeros and ones, and one thing I can do is to just move a sliding window, right? I have a sequence of ones and zeros. I take, say, 1,000 or 100, and I label it this vector of length 100 with 1 or 0. Now it becomes a binary classification problem of a binary vector. So this is a huge space. I've chosen to dimension it at 100, but each point here is being binary labeled as 1 or 0. Fine, so I have this data. And now you feed into your favorite machine learning algorithm. Try support vector machines, space classifiers, neighbor classifiers, neural networks of, the feed-forward networks that I used, your grandmother's kitchen sink, whatever. Try your favorite thing and throw at this problem. Okay. To make it even more regularized, take 50,000 samples, for example, and do 2080 cross-validation, and record its precision. And what's called MCC is essentially square of the chi-squared. And you want both of these numbers to be close to 1. Right? So now you throw any of these things to the 3 problems that I mentioned earlier. This one, a simple neural network can instantly recognize the 100% accuracy that is what it is. It's what it is. Okay, it's trivial. Essentially, any linear layer in your neural network will recognize you're doing a linear transformation. Prime test is a little bit more difficult, but it's not completely random. It's doing a little better. Maybe it's kind of using a SIF method. It's kind of recognizing maybe every 3 there's a 1, every 5 there's a 1, every 7 there's a 1, so on and so forth. Or there's a 0 because it's not a prime. And the Liouville lambda function is, you can see here, 0.5, so 50% accuracy, and 0.001 chi-square. What that means is completely randomly guessing. It's a coin toss. That, in other words, at least I haven't been able to find any neural network that can say anything about the Liouville lambda function, which is good, because if we break that, and then I can break every bank in the world, and then you won't see me anymore, right? I mean, that is really equivalent to this problem. If you can tell me what the next number is with 100, well, even better then, if you can even tell me this at 51% accuracy, you can start breaking banks. Because this sequence includes the properties of prime factorization. So it's kind of reassuring that neural networks can't do better than humans. But, well, okay. But I'm not saying that it can't, right? But, so whoever disappears from this conference, we know what you're up to. So since 2017, I've been exploring this problem. So I owe a great gratitude to my many fantastic students. I think one of my visiting students, Antoine, is here in the audience, and my wonderful collaborators, to try to study what mathematics is from that point of view. That was just enticing you to think about mathematics from the point of view of neural networks and machine learning. So now let me just get a little more philosophical. Right? What is mathematics? And I think I can try to at least attempt to answer it at 3 levels. Right? Level 1, and this goes back to Russell and Whitehead. So Bertrand Russell and Whitehead, Bertrand Russell is, of course, one of the greatest philosophers and logicians of all time. He wrote Principia Mathematica in the 1910s, inspired by Leibniz in the 17th century and Frege in the 19th century to axiomatize mathematics. So what do you mean by axiomatize mathematics? Well, you write sentences. If you read Principia Mathematica, it's just logical symbols, logical symbols, logical symbols, and then you fall asleep. But computers don't care. They can just keep on reading logical symbols. So what Russell and Whitehead were hoping for is that at some point, all of mathematics will be reduced to logical symbols. And in fact, all of reasoning, and in fact, all of science. In fact, everything that we do can be reduced to this, right? To this computing community, this is certainly true, right? I mean, all of physical reality is just a sequence of sentences. But that program, unfortunately, was completely killed within 30 years. And that program was killed because of Gödel, Church, and Turing, because these 3 guys proved there exist sentences within mathematics whose proof could lie without mathematics. In other words, there exist undecidable statements in mathematics. So this is called the Gödel incompleteness theorem. So there exist theorems which are neither true or false within any logical system. So this paradigm of Russell and Whitehead was killed within 30 years. But it did not stop this very great program, which is called the ATP program. This is automated theorem proving program, which is still very much alive. So I like to quote my friend Min-Young Kim, who's a very distinguished number theorist. He says, the practicing mathematician hardly ever worries about Gödel. Just because in sentence number 3 trillion is undecidable doesn't mean that there are trillions of other very interesting statements in mathematics, in science in general. And that's fine. So mathematicians have been working since at least 1956, which interestingly was the beginning of neural networks. This is a completely different direction, but it just coincidentally started in the mid-50s, to start proving theorems of mathematics using automated theorem provers, which is exactly what it is as it promises to do. Sentence, sentence, sentence. Can you start then deducing every intermediate step of every single proof? All right. And of course, since mathematics is a language of science, can then all of science, all of human reasoning be deduced to this? And this is going very well, I must say. So Kevin Buzzard, who is a great proponent for this, I won't bore you with the details of these programs. You can play with them. They're online and freely available. Have been given to the ICM addresses, the International Congress of Mathematics Conference, just the last couple of years, is that this computer-assisted proofs is very much going on. Now they have the database of every undergraduate level mathematics in this language in the computer, a couple of million lines of code. And now they've checked the consistency, so everything you've been taught as an undergraduate in mathematics is so far correct. I will tell you about what's not correct over coffee, and if you're interested. So of course, this is very much in collaboration with Google DeepMind. So DeepMind Our friend Shagadi, for example, or at DeepMind says, well, they're very optimistic, right? So DeepMind beat humans in chess in 90s, computers, and then DeepMind beat humans around about 2018, and their projection is by 2030, DeepMind, which is the next one. So we've had AlphaFold, right? We have AlphaZero. The next big program in Google is AlphaMath. And their prediction is that AlphaMath would generate new theorems by 2030. I think it's a bit too optimistic, by maybe 2050, which is kind of nice. So this paradigm, I'm going to call this bottom-up mathematics, because you're trying to build mathematics line, sentence by sentence. We might not entirely be ready for this yet, because it may take another, by 2050, maybe 2000, 2100, we'll start getting new theorems. But we are ready for the second, this paradigm of mathematics is. So let's go back to mathematics. Typically, the mathematician does not do mathematics in this way. Even though it's presented in this way in the style of Russell and Whitehead, that mathematics is done from definition, lemma, theorem, proof, corollary. If you read a math book, that's how it's done. But this is simply not how mathematicians actually work. We don't do that. We play first, and then we write it backwards. Every single math paper you've ever read in your life, or in fact, every single science paper you've ever read in your life is written backwards, right? Because you try, theory, I don't know about experiment, but in the theoretical sciences, you do backwards. You experiment first. You fail, you experiment again. And then, once you have something that feels right, you try to prove it, and then you write your papers backwards with definition, right? So this is nice, because this is how mathematics is presented. But how mathematics is actually done is exactly the opposite direction. So historically, I would call that was top-down mathematics. Intuition. Fuzzy, warm feelings of what things might be. So let's just give you an example. There are countless examples. For example, calculus existed with Newton and Euler long before analysis even taught us how to do calculus properly. They never worried about convergence, right? Algebraic geometry existed long before the 1960s, the French school, Bourbaki, just because people were, Descartes was playing with curves, they were drawing stuff. To give a great example, this is a joke I use. I think it's an overused joke, but I say this joke in every one of my talks, so it's okay. If you've never seen this joke before, it's great. So what is the best neural network of the 18th century? Well, it's undoubtedly the brain of Gauss, right? That neural network, in the form of a human mind, that mind was possibly and arguably the greatest mind that ever existed, because just to give you a power to appreciate that mind, this guy at the age of 16 looked at this curve and said, that's clearly x over log x, because he was bored. By the age of 8, he was able, this is a famous story, the school was in trouble, the professor says, the teacher says, you add up 1, 2, 3, 4, add it up to 100, and Gauss said, the kids were doing there, hours later, Gauss said it in 1 minute, the answer is 5,050, because he added 1 to 100, 2 to 90, and then divided by the, So that's at the age of 8. So by the age of 16, he was able to do this. He looked at this. What is this? This is a plot of the number of prime numbers less than a given real number x. This was called the prime counting function, pi of x. He looked at this and he said, this is clearly x over log x. Why? Nobody knows. Because he had the intuition, the experience, and the sheer genius to just spot this pattern. And now it was proven 50 years later in the 1860s by Adamard and Delaveille-Poussin using complex analysis. Gauss was able to conjecture this without 50 years before complex analysis was even invented, just because he could. Right? So this top-down version of mathematics is actually, I'm going to give you more examples. For example, the famous Birch-Swinnerton-Dyer conjecture, which is one of the Millennium Prize problems, 1 million price tag. It's one of the biggest problems in number theory. That was done just because Birch and Swinnerton and Dyer in the 1960s, they were bored. They were working in the basement at Cambridge, with the first generations of computers. They plotted a bunch of stuff, and they said, well, it's fine, it's what it is. And I will explain the BSD conjecture over coffee later if you want. But the point is that that's actually how we do mathematics. We look at data, and then we try to formulate conjectures. We don't write our papers that way because it seems very embarrassing for us to write it that way. But it's okay, I'm just telling you the trade secret. I'm going to get shot, by the way, outside by fellow mathematicians. But this is actually how we do things. So this kind of experimentation is very interesting because it gives us a lot of, well, it's almost a new type of data. It's called, well, I mean, it's mathematical data. It's noiseless data. It's the kind of data, NH data is filled with noise. The data which, to which we apply machine learning, it's always done to noise-full data. But mathematics data is now ripe. They're terabytes and terabytes of this stuff. So if I give you 100,000 cases of stuff that I mentioned like this, whether it comes from combinatorics or number theory, can you start predicting what Gauss was doing when he was 16? Of course, all of the easy problems have been done because there are a lot of clever people. But now we have something else that even Gauss could not done, which is hundreds of neurons, hundreds and thousands of neurons linked together to try to conjecture something else. So this is fine. Can you start pattern spotting, and can you then conjecture and then prove a formula? So this is type 2 mathematics. And then to me, I also find it interesting, can you, by looking at 100,000 cases of such data, tell me which branch of mathematics is likely to come from? Geometry, or number theory, or combinatorics, or topology. But, okay, so this is the kind of things you do. So just to give a quick example, this is the sequence of the primes of labeled, so black dot is, a black is prime, white is not prime. I've broken up to like 50 and I've done this. And you can, this red square, of course, is a convolutional window. Can you start, for example, do this? It's a nice diagram. You'll see it again later in a book cover. And this kind of challenge to do is to study whether whether this kind of structures can pick out the problems of primes. And the thing that I mentioned earlier about the Liouville lambda function, so this is actually a famous problem in number theory. It's called Sarnak's challenge, and I think he will actually give you money if you can find a neural network or whatever, find some methodology which you can tell what the next block is, whether the next block is white or black in the sense of the Liouville function. And you can play with other things. In group theory, for example, if you're interested in this thing, I've been playing with Mignon actually, which gives us ideas of whether you can predict in group theory. One of the very important things to study is whether a finite group is simple or not. And one of the things we did was just to plot the Cayley multiplication table of such groups in this huge dimensional space. And then a support vector machine was able to distinguish this, to 97% accuracy, which is quite. And there's no theorem yet to even. There's not even a methodology to approach a problem in representation theory in this way. So this is just a couple of examples, and I won't bore you with this. So this paradigm, just to summarize, is clearly useful for mathematics and physics, this top-down level of mathematics, right? So I've told you about bottom-up, which is automated theorem proving, which is clearly useful. And then this top-down approach is also, they're so complementary to each other. Bottom-up is ATP, and it's very computationally expensive because you have line by line of all of the structures of mathematics. Top-down is much more playful because you can make errors, but if you make errors, you should guide yourself towards finding the right path of finding the correct conjecture, and then you prove it with traditional mathematics. So, of course, this kind of ideas can speed up mathematics a lot, and one of the things over the years, you can formulate various conjectures. There was a nice paper just last year by DeepMind, which is that they found various volumes in this branch of mathematics known as knot theory. So that's 1 and 2. I promised 3, and I'll just finish up now with number 3 of what mathematics really is. Well, mathematics is a natural language, right? Because it has, right, almost by definition. So there is this wonderful paper, or this is a PhD thesis called, The Language of Mathematics. But of course, this is really an echoing what I mentioned earlier of works of Russell and Wittgenstein of what the structure of mathematics is. But for this crowd, it is a computational intensive crowd. We should look at mathematics as a natural language. So one of the first experiments on this, of course, is to use a large language model on the archive. Where, if you guys know the archive is a repository of preprints of everything that's published. So what's kind of interesting about the age of data is that not only do we have mathematical data, we also have the repository of the entirety of the corpus of mathematics in every field, including theoretical physics, computational biology, computer science on archive, right? So that's about, on the order of 1 to 10 million articles, and you can just scale up, of language. So one of the early experiments that I did was to take some of the fields that we're familiar with and just embed that into a vector space of NLP. So word-to-vec, and I was able to find syntactical identities on what is something very interesting in the structure. This is not too different from this Nature paper where these guys they took the abstracts of the entirety of the field of material science, and they were able to predict many more reactions that are much more efficient simply by looking at the language of the abstracts, which is kind of interesting. So this begs us to think the third and final way of how we do mathematics, and indeed how we do science. And how do we do science? We take a paper, we read the title, we might read the authors. In fact, we might even decide at that point whether to read the paper or not. We read the abstract, skip everything, read the conclusions if we even get there. So most likely, science is progressing by people reading just the abstract. And this is the entirety of this field of science. If you learn the language of that, you will learn the language of science. Right? And that's within reach now. And the reason ChatGPT 4.0 is doing so well in mathematics is because it's learning something. Is learning the structure of the language of how it's presented. And of course, it gets stuff wrong, but it doesn't matter. So do scientists. But I'm a big proponent for this kind of exploration. I think AI mathematics shows not so much. People get scared, about AI and stuff. People are scared because are they going to take over? Is AI getting so intelligent? I'm not afraid of. I think the problem is it's not so much that AI is so great. Why is AI doing so well? It's not because AI is so intelligent, it's because humans are so stupid, right? Comparatively. And most of us do, like the philosopher Dennett says, we do almost everything by competence without comprehension, which is what humanity is in some level. So if you want to read more about this, I highly encourage you to buy this book so I can get the £5 royalties a year. So I can buy myself a lunch every once in a while. But that talks more about this. And then this one, this one doesn't have a QR code, but this is just about to appear this week. And I think Laurent there's from World Scientific, and that has this picture about the primes. The cover is a challenge to understand. So I think, and of course, if you want to submit, there's this new journal with World Scientific, which kind of calls for how to do data exploration in mathematical sciences. So thank you. I'll stop there.